And for chapter 4, we're going to start with forces in one dimension. So we're only looking at forces basically that are going either vertically or horizontally. Okay, we're not going to deal with angles yet. We'll do chapter 5, which has to do with forces in 2 dimensions, so forces that are applied at angles. And that's when we really have to start breaking things into components and working on a vector addition a little bit more. But chapter 4 is going to be just forces in one dimension, so things that are purely vertical or purely horizontal. Okay, so we'll take a kind of chapter 4 and 5, we'll kind of get grouped together for the rest of this semester. Okay, we'll take chapter 4 and 5. So. Okay, force. Can anyone tell me what a force is? We looked at vocabulary last class. What's the basic definition for a force? What, Yvonne? Yeah.
Can be a push or pull, and it's something that you can see or touch, but cannot always see in action.
Perfect. Okay, a force can be a push or a pull exerted on an object. So we see those in lots of different situations. You see forces all over the place. And hopefully as we work through this chapter, you'll start being able to see kind of where you can see forces in real life a little bit more. Okay? How do forces affect the motion of an object that it acts on? Okay, so if I'm applying a force to something, what could I get that object to do? Move, right? Could I get it to speed up?
Yes.
Okay, could I get it to slow down?
Yes.
Or come to a stop?
Yes.
What about if I push something to the side? What does that make it do? Change directions, yeah, or start in motion. Okay, so basically forces allow objects to speed up, slow down, or change directions. Okay, or change directions. So those are the things that forces can do to an object. All right. We looked at these two vocabulary terms also. A system is the object that is being manipulated, and I think some of you didn't quite get that on your vocabulary assignment. Okay, I think you were taking Google's definition of a system rather than reading in your textbook for the definition of a system that applies really to physics. Okay, I kind of got that vibe from some of your answers on your document, okay, and your picture descriptions. So the system, in terms of physics and in terms of forces, is the object that's being manipulated. The agent is the thing or the person or whatever that is causing that force or causing that motion. So if I'm sitting here pushing this handbook, what is the agent and what's the system?
Agent is the book and you're the system.
Other way around.
But
I am the agent. Right? The book is the system. So yeah, you could say my hand is the agent. Realistically, I am the one that's doing the moving. So you don't have to get super specific with the agent, but just kind of pay attention to that. Agent is the one that's doing the work. Okay, system is the one that's being manipulated. There's a couple different types of forces, and what do we know about a contact force?
It's where you make contact with another person.
Yeah, that's it. You have to make contact. So when I was pushing that book back and forth, that was an example of a contact force. Most forces that we think about are contact forces. Okay? They're when two objects collide and they put one or the other into motion. Okay? So most of the things that we think about are contact forces. Okay? Pushing, pulling, anything that comes in direct contact. When the system and the agent come into direct contact, we consider that a contact force. Okay? A field force, however, is, can anyone tell me? Field force?
vector field that describes a non-contact force.
Okay, non-contact force, we're not coming into contact. So these are forces that are exerted without contact. Can anyone give me an example? Magnetism, good. Anything else? Yeah, Ivanka? Gravity, perfect. Okay, and maybe one more? Wind or air resistance? Yeah, very good. Good. Okay, those are things that we can consider field forces, like air resistance or drag force, things like that.
Could.
Okay. If we drop anything on the floor, gravity does not have to come up and pull that object down, right? We don't see the floor come up and pull that object to the floor. Our gravity just pulls it down. Okay, so no contact. All right, we talked about other field forces already. We're going to talk about the diagram here in a second, so don't worry about that. Okay? This document I have printed for you here, and this just kind of gives us lots of different types of forces and the symbol that goes with them. So I want you to complete this table. I did some of them for you. I just blanked out a couple important ones that I want you to write down so you get some familiarity with those. These are different types of forces that we will use throughout chapters 4 and 5. Okay, so go ahead and get this table completed in your handout. You need one more. Okay, so when we look at motion diagrams of forces, we draw something specifically called a free body diagram. Okay, so these free body diagrams are how we depict forces. Okay, free body diagrams are how we depict forces. So these give us kind of a pictorial model of what we should be looking at here. So let me give some examples about what's happening here. Can we see this picture? Right here, we've got a hand applying a rightward force on the book. We have gravity that's always acting on that book. And then we have a force that's, they labeled table on book. What would be another name for that upward force? The normal force. Okay, so let's look at basically how we will label these. I don't need subscripts that are 3 words long. Okay, we don't need that. Okay, so our force here, this is our normal force because it is the surface exerting a force upward on that book. So the normal force always comes from an object that's resting on a surface. So if something is on a surface at all, that could be the ground, that could be the roof, could be resting on my hand, resting on whatever. Okay, as long as it's on a surface, it's going to have a normal force. What would we probably call this force right here?
Gravity.
Gravitational force. And how do we label that? F sub g. Good. And then here we could leave that if we really wanted to. I don't like to do that. I like to label these as F applied. APP. We're applying a force there. Okay? And there's, you could label it F sub, I'm sorry, what? I'll almost always label it as F applied because we are applying some sort of force. Okay? So the object or the point of these free body diagrams is for us to identify every force that's acting on this system, right? And the system here would be the book. What would the agent be? The hand, right? Or the person. Yeah, that's fine. Okay. Your book tells you to circle the system when you draw free body diagrams. We really don't need to do that. Okay. When I draw a free body diagram, it looks just like this, right? Our system just becomes a dot. You don't need to draw a fancy picture if it's a car or whatever like that. Just go with the dot. And then we identify every force or every place that our object is touching the outside world. So every force that's acting on that object. We have to draw our forces as vectors. What does it mean when we say it's a vector?
It has
Direction and magnitude. Good. Vectors must have magnitude and direction. So that means that we have to draw these vectors to scale. Okay, does that mean that we need to get out a ruler every single time?
No.
Probably not. But if one force is twice as large as the other, that means we need to draw one of our vectors twice as large as the other. Does that make sense? Draw them to scale relative to each other. Okay? Once your forces are drawn, you can identify the object as a dot. So like I said here, we didn't need to draw the whole book. We just identify our system or our object as a dot. Okay, so here's our system. We've got 3 forces that are acting on it. Something else that you need to know about free body diagrams is that your vectors never go into the system. So we're applying a force to the right. That does not mean our vector looks like this, right, into the system. All forces need to be going outward from that system. Okay, does that make sense? Outward. So just because we're applying a rightward force does not mean that our free body diagram would look like that. We want our forces to go outward. So we're starting at the system. It's a rightward force, so I'm going to draw my vector to the right. In these free body diagrams, each single force needs a label, whether that's normal force, gravitational force, applied, friction, air resistance, whatever it is, you have to label that force.
So are we gonna have it where it's like,
Okay, remember each force vector should be drawn to scale and force arrows should always be pointing away from the object. So when you draw that vector, we want the tip of that vector away from the object. Okay, no vectors into the system. Okay, so let's just try a couple practice objects. So let's say that I have a mug resting on a table. Okay, so I have a mug that's just resting on a table. That's it. No one's pushing on it, no one's pulling on it. Okay, so I want you to start thinking about how many forces would be acting on this object. Okay, so I've got a mug resting on a table. What sort of forces would I have acting on that object? Eric, give me one.
yeah, friction normal?
Normal force. So the F stands for force. So the normal force, which direction should it be pointing? Up, right? Or perpendicular to the surface. That's important. Sergio, what's the other one? Gravitational force. Okay, so when I label them, I have FG and FN. Okay, yep.
You said not to draw it.
Yeah, you don't have to draw the picture. All you need is like this. Yeah. I just wanted to give you a little visual representation. This is what the free body diagram itself would look like. That's it. Okay. All right. Let's say now that I am applying, let's say that I have a box on the ground and I'm applying a leftward force against friction. So I'm applying a leftward force and we need to consider friction here. Okay, so Sarah, can you give me one of these forces? Okay, friction, and which direction would my frictional force be going? If I'm pushing to the left, rightward, there we go. Okay, and we label that F sub little f. Okay, Keaton, can you give me another one?
F applied.
F applied, and which way would it be going?
Left.
Left, good. F applied. Okay, Brendan, can you give me one?
I zoned out. I have no idea what the question was. I'm sorry.
Okay, we're applying a leftward force on a box on the ground.
Okay, so the box would have weight. So
Okay, and what would I label that force?
FG.
FG, good. And Candace, can you give me the last one? Normal force, good. Good. For this stage of the game, right now, today, we don't know if the applied force is greater than the frictional force. We don't know if the object is moving vertically just yet. So right now, we don't have a scale really to draw to. We'll start looking at Newton's second law, which deals with the net force, and then it will tell you maybe the frictional force should be shorter than the applied force. Okay, or maybe the gravitational force is longer than the normal force, things like that. We're going to have to start thinking about that. Okay, let's think about this though. Is my box in this scenario, is my box accelerating in the vertical direction? Is it moving vertically at all, you think? No, it's sitting on the ground. I'm pushing it horizontally. So if it's not moving vertically, shouldn't my vertical and shouldn't my upward and my downward forces be equal to each other? Yes. Yeah. So you could say like that. Okay. All right. Let's move on here. We're going to talk about something now called the net force. Okay. What does it mean if you have a net, really, of anything?
Overall,
Yeah, overall, is that what you're going to say?
yes.
Mm-hmm. Net is, yeah, that's what it is. If you have a net profit, that means your profit minus your expenses, right? Your in minus your out. So that's what we're looking at here with net force. We're going to look at our positives minus our negatives. That's our sum of all forces. Okay? Positives minus negatives. So you might want to even write that down. Okay, positives minus negatives. Okay, you can write it out in real words. That's fine. But let's think about it in terms of our upward forces minus our downward, or our rightward forces minus our leftward. Because we're going to use that same coordinate system, right, where our positive directions are up and to the right. Our negative directions are down and to the left, just like any coordinate system that we've used so far. Okay. something that we need to understand about the net force or about an object, we consider it to be at equilibrium when all of our forces cancel out. Okay, so that means when it is at rest or when it's moving at constant velocity. Those are two situations in which our object is considered at equilibrium, which means our net force is equal to 0. Okay, and I'm going to explain this much more here in a second, but I want you to understand. So when I label it F net, that means I'm talking about the sum of the forces of that entire system. Okay, either vertical or horizontal. We don't mix the two. So I'm thinking here about either all of the vertical forces or all of the horizontal forces. And my net force, or my overall, which I label F net, is equal to 0 when an object is at rest or when it's moving at constant velocity. Okay. I will explain why constant velocity gives us a 0 net force here in just a second. Newton's second law will help us explain that. Okay. So let's talk about how we calculate the net force. Okay. When finding the net force of a free body diagram, that's what that stands for, take the up forces minus the down forces and right minus left. Okay, right? We're taking positive forces minus negative forces when we're trying to calculate the net force. Does that make sense? Okay, so let's take a look at this first free body diagram here. Okay, right over here. Here's our system. We've got a leftward force of 100 newtons and a rightward force of 100 newtons. Okay, so if I take my F net, I'm going to take F1 because it's the rightward force minus F2, which is the leftward force. Does everyone see where those came from? Right? My F net is my overall, and I'm going to take my rightward forces minus my leftward forces. And if I say 100 minus 100, that means my net force is 0 newtons. Okay? This capital N is newtons. That's our unit for all forces. So you might want to write that down as well. Okay? Capital N is Newton. It's the unit for any type of force. Okay, that one seems easy enough, right? Equal forces but opposite directions, kind of like a tug of war situation, right? Both teams are pulling with equal force, so that that middle is not going to move at all. Okay, we can think about it like that. My second free body diagram, I have two forces. To the right, 100 newtons, and also to the right, 100 newtons. So when we add these vectors tail to tip, we basically got F1 plus F2. Okay, so if I add those tail to tip, that means when I set up my F net equation, F net, since they're both going to the right, I would take F1 plus F2. Do I have any forces that are going to the left in this situation? No, so I could either put minus 0 just to show myself that I accounted for it, or you could leave that off, either way. Okay, so my net force here is 200 newtons. Yeah? I know this seems really simplistic. I understand that. But it will get more intense. So I just need you to make sure that you understand the basics of it. Okay? Net force in this situation, I've got 200 newtons to the left and 100 newtons to the right. So when I set up my net force equation, I would say F1 minus F2, which gives me 100 minus 200, which gives me a negative 100 Newton force. Okay? Or to the left. You could say it either way. Yeah, so they set their F net as 100 newtons left. You could tell me that either way. Either by giving the negative or by saying leftward or whatever. Okay? Okay, so let's go ahead and try this free body diagram on your own. It's accelerating to the right. You need to include friction. So try and figure out what that accelerating means, and if not, I'll explain that here in a second. So let's take a look at our free body diagram here. We've got an applied force. We've got a gravitational force. We've got a normal force. And we've got a frictional force. Okay, so what do you notice about these two forces here?
Friction is smaller than
Friction is a smaller force. And we know this, it has to be smaller because it says it is accelerating. Okay, we said it is accelerating to the right, which means it's got a positive net force, right? Our net force should be to the right. If it was moving at constant velocity, what do we know about our net force of something at constant velocity? It's 0, right? So if it was moving at constant velocity, our net force would have to look something like, or our free body diagram would look like that. Those two would be equal to each other. But that's not the case here, okay? So our horizontal forces tell us a little bit of something about this accelerating part. What about our vertical forces? Are they equal to each other?
Yes.
Yes. Okay, so you could put the little congruent line if you want to. You don't have to. That's up to you. Whenever an object is just on a surface, right, it's not moving up and down, accelerating up and down, that means that the upward forces should equal the downward forces. Okay, upward should equal downward. Do we need to have any connection between our vertical and our horizontal forces? No. No, 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 no. Okay? Very good. Okay, a book is sliding to the left on a table. Ignore friction. So let's try this one. Book is sliding to the left on a table, but ignore friction this time. Okay, so a book is sliding to the left. We're going to ignore friction. How many forces do we think we have? Miguel, what do you think? 3. Very good. Okay, Miguel, can you give me one?
Force applied.
Okay, and which direction is it going? Left. Does it matter how long it is? No, it really doesn't matter. Okay, Sarah, can you give me one?
The weight versus gravity.
Mm-hmm. F sub G. And Sydney, can you give me the last one?
The
Normal force. What do I know about the normal force? It should be equal to the force of gravity. Oops. Okay, it should be equal to the gravitational force. And we know that because our book's not accelerating in the upward or downward direction. A stone is falling at constant velocity. So you can label it as F sub air if you want. There's a couple different ways you can do that. Okay. Okay. Wyatt, can you tell me how many forces you think we have here? 2. Good. Can you give me one of them?
I put FA.
Okay, for air. Good. Okay, Eric, can you give me the second one? Gravity. Okay, and what do we know about these two forces? They should be equal to each other. And why is that the case? Because it's moving at constant velocity. Okay, constant velocity tells us that our net force is 0. So if I were to take my net force equation here, it would look like this. F net equals air minus gravity, right? Because we take upward forces minus downward. This should be 0, which means FA minus FG. And I move that to the other side, which means FG equals FA. Okay, so mathematically it shows you that. Okay? Okay, Newton's first law here tells us an object at rest will remain at rest. An object that is moving will continue to move in a straight line with constant speed if and only if the net force acting on that object is 0. Okay, what's the shortened version of that? That's right. An object in motion will stay in motion, or an object at rest will stay at rest. Okay, you can write the abbreviated version down. That's fine. You don't need to write this down word for word. Okay, an object at rest will stay at rest. An object at motion will stay in motion unless an outside force acts upon it. Okay, that's another kind of way to say that. Okay, unless an outside force acts upon it. This is Newton's first law, and it's called the law of inertia. Hopefully you've all heard that before. Okay, Newton's second law tells us the acceleration of an object is equal to the sum of the forces acting on the object divided by the mass. Okay, and this is really what you need to take away from that. Force equals mass times acceleration. Okay, this is what it said in words. And this is how we translate it because we use it like this the most often. So it's F net equals mass times acceleration. This equation you will use all the time. Okay, so if you want to get out an equation sheet, this is the first one for chapter 4 that you really need on there. Okay, or if you want to come grab a new equation sheet, you can do that as well. Okay. So F net equals mass times acceleration. What are the units you think for net force? Newtons. And what are the units for mass?
Grams.
Kilograms. Units for mass have to be kilograms. What does acceleration units need to be in? Per second squared. Very good. These have to be true in order for anything to come out in newtons. Okay, because a newton is in and of itself a kilogram times meters per second squared. Okay, so in order for any of our force equations to work, we have to have mass in kilograms. We have to have acceleration in meters per second squared. Okay. We just talked about this. Okay, great. Newton is a capital N. So please don't label your forces with a lowercase n.
What is it?
A lowercase n?
No, I mean like
Oh,
for science
like-
purposes.
it stands for nano, but I don't think it's anything of itself. Or the mountains. Okay, let's try some here with our net force equation, or our Newton's second law equation. Estimate the net force needed to accelerate a 1,000 kilogram car at 4.9 meters per second squared.
Items. Yeah, 4,900.
Let everyone else get there. Keep in mind that with this problem, we're not exactly able to draw a free body diagram because we don't know, is friction acting? Is it not? We don't know, okay? But all we know is that with or without friction, this object is accelerating at a rate of 4.9 meters per second squared. So we only are worried about the net force here. We're not worried about frictional force or applied force. We're talking about the net force, okay? So when we take F net, we should take our mass times our acceleration, and we get an F net equal to 4,900 newtons. Okay? And is our net force in the positive direction or the negative direction? Positive. Why is it in the positive direction? Yeah, because our acceleration is positive. Okay? Take that into account. Our acceleration is positive. So if it has a negative acceleration, that means it's accelerating in the negative direction, or it's accelerating downward. Okay? What net force is required to bring a 1,500 kilogram car to rest from a speed of 100 kilometers per hour within a distance of 55? You need to use your kinematics equations first. Okay? So get this written down if you need to. Get whatever written down you need to. I told you we would use kinematics all the way till the end of the year. Okay? I wasn't kidding. So let's talk about some things that we know from this problem. Okay? We are trying to solve for net force. Okay, so our net force, we don't know. We know, what does this value tell us? The mass. Not the weight. Mass and weight are two different things. Be careful about that. Okay, what does this tell us right here?
Zero.
Final velocity, because it's going to rest from a speed. So final velocity is 0. Initial velocity is... Do we want things in kilometers? Yeah, we need it to be in meters per second. So we need to take 100 kilometers per hour times the shortcut. Right, 27.78 meters per second. Uh-huh. You need to be able to do that. Am I moving too fast for you? Or are you good converting kilometers per hour to meters per second? Okay. And we also know our distance. It's 55 meters. So what kinematics equation can we use to solve for the acceleration? Uh-huh. Good.
Equals that, yeah, that one.
Good, the third. We want to use the third equation. VF squared equals VI squared plus 2A dF minus DI. Okay, the reason that we need to solve for acceleration here, because we have our mass, we're solving for F net, we don't know our acceleration, but we can solve for that using our kinematics. Okay, so let's see here. VF squared, so 0 squared equals 27.78 squared. Do not plug in 100 there. Okay, I want you guys doing this math.
10,530.
Okay, so our acceleration comes out to be negative 7.02, and our net force is negative 10,000. Say it one more time.
530 newtons.
Okay, so let's think about this. If our car is moving and our net force is negative, what type of force might that be? Could be friction, could be air resistance, the brake, could be an applied force, right? That's a brake. There's lots of different ways that we could slow down that car, okay? But over 55 meters, it slows down at that rate, that negative 7.02 meters per second, and that means this is the overall force that's happening within that system. If you want to try this one on your own, feel free to do that. If not, I'm going to keep going through this for people that are still needing a little more practice, which is just fine. Okay? I'm going to always start with a free body diagram if I can, and in this case I can do that. Okay, so I've got gravity acting on my car. I've got a normal force. I've got an applied force, because it asks me what force is being applied. And I've also got a frictional force. Okay. So now, there's my free body diagram. I know these two forces are equal to each other, because my car's not accelerating in the vertical direction at all, right? It's only moving horizontally, hopefully. Okay. What force is being applied to the car? So we don't know this force. We know that we have 300 newtons of friction. Okay, so this is how you start these problems. We start with our net force equation. And when I say that, that means we're going back to when we subtracted the positive forces from the negative forces. So there are two ways to solve for net force. One of them is taking mass times acceleration. One of them is taking rightward forces minus leftward, or positive forces minus negative forces. Does that make sense?
Yeah, the first one on this, what would you do with the 300 units of friction?
So that's what we're going to do. We're going to say force applied minus 300 newtons, right? Because this is our frictional force. So force applied. But now, what do we know our net force? Can we do a substitution here? Don't we know that F net is also equal to mass times acceleration? So can't I plug that in right here?
Yes.
So I'm going to say mass times acceleration equals force applied minus 300, which is our frictional force. Okay, is everyone on the same page up to this point?
Yeah.
Okay. Do I know my mass? And I know my acceleration? 3.12 equals force applied minus 300. You could also solve for F net, by itself and then just plug in the number here. You could do that too. It doesn't matter what order you go about these problems. There's lots of different ways to kind of get to the final answer, but okay, so we're going to multiply these two.
6,240
Equals force applied minus 300. So I add my 300 to the other side, which means my applied force is equal to 6,540 40, okay. Okay, so is my frictional force greater than my applied force here?
No.
No. My applied force is larger, right? So does it make sense that my acceleration is positive?
Yes.
That my object is accelerating?
Yes.
Okay, if my applied force and my frictional force were equal to each other, what would my acceleration be?
0.
0, right? I have constant velocity. Good. Very good. Using Newton's second law, what's the net force of an object moving at constant velocity?
0.
0. Okay? So I told you that anything at constant velocity has a 0 net force, but this is why. F net equals mass times acceleration. If I'm moving at constant speed, that means acceleration is equal to 0. So anything times 0 is 0. So that's why that works. Okay? Constant velocity means 0 acceleration. Okay.